As I mentioned the other day, spatial autocorrelation is about the combination of attribute similarity and locational similarity. We saw that we formalized locational similarity with a weights matrix, attribute by means of a number of different functions, cross product, square difference, absolute difference. And there's a difference between global spatial autocorrelation, which is an attribute of the pattern as a whole. And the way to think about it is it's one number for the whole data set. And then next week we'll look at local spatial autocorrelation, which is about specific locations. And so in an exploratory sense, local spatial autocorrelation is more useful because it brings up hot spots, cold spots, those kinds of things. Global spatial autocorrelation is more appropriate in a diagnostic sense, in a regression context where you look at the residuals of a regression and you want to make sure that they're not correlated or not otherwise systematically related. But nevertheless, it's a very important concept as a start because you can't really do local correlation without having a good handle on what global spatial autocorrelation is about. So there's a lot of stuff here. This is one of my 70-slide dealios, so I'm going to have to speak very fast. Actually, seriously. So I start with two classics, Morans Eye and Geary-C, which are kind of like the best known measures for spatial autocorrelation. And then we go into a way to visualize these, which I call a Morans scatter plot, because the Morans scatter plot action global statistic and then the local statistics that we'll talk about next week. And then I cover two different perspectives. So the Morans Eye and Geary-C are tightly connected with the weights matrix. And then we step away from the weights matrix and look at distance as the organizing principle. And we still have attribute similarity and we still have locational similarity, but now locational similarity is organized by increasing distance of pairs of observations. And the similarity between the observations is either in product form, which is a correlogram, or in square difference form, which is a variogram, which is at the basis of a lot of geostatistics. And so these are all, if you wish, different faces of spatial autocorrelation. They all deal with the same problem, how to combine attribute similarity and location similarity in some kind of a summary way. So we saw this a couple of times already. One statistic for the whole pattern, and very importantly, not clusters, but clustering. And so as we saw last week, the point of departure, the null hypothesis, is the absence of anything. It's spatial randomness. So we want a statistic that allows us to reject that null hypothesis in favor of either positive spatial autocorrelation or negative spatial autocorrelation. So Morans Eye is arguably the most commonly used spatial autocorrelation measure because, in my opinion, because it has a direct connection to a notion of a linear relationship, as opposed to Geary-C, which we'll see in a few minutes, which is based on square difference, which I have to be honest, confuses a lot of people. It's actually not confusing, it's just the reverse. You know, if you have product, it's similarity. If you have square difference, it's dissimilarity. So it's the other way around. But whereas for Morans Eye, a positive number means positive spatial autocorrelation, for Geary-C it's the other way around. So a negative number means positive spatial autocorrelation. And a lot of people get kind of thrown off by that. But once you know it, all you have to do is change the sign and it's the same. So this is a cross-product statistic. So the measure of attribute similarity is the product between the values at two locations in deviations from the mean. Why in deviations from the mean? Because these spatial autocorrelation statistics make two very important assumptions. One we get rid of very easily is the assumption of a constant mean. So if you express everything in deviations from the mean, then the new mean is 0, so it's constant. You don't have to worry about it. The second assumption is constant variance, and that is actually quite a bit more difficult to deal with. And we've already encountered situations where this plays a role, namely when we were doing maps for rates or proportions. We saw the intrinsic variance instability that is part of a proportion and how we can deal with that by smoothing the rate. And so if we do spatial autocorrelation of rates, our little red flag should go up and say, hey, wait a minute, the variance is not constant. This is not really appropriate. And so we'll see in these extra notes that there are ways to deal with that. But importantly, strictly speaking, the inference for these statistics only works if one, the mean is constant, which we deal with by taking deviations from the mean, and the other one is that the variance constant. So numerator, we have a double sum over, so basically all the pairs of observations, Zi and Zj. These values are multiplied with each other, but as I mentioned the other day, they are pre-multiplied by the weights. So only if the weights are not 0 do these cross products actually count. So when they are not neighbors, I and j, the product can be whatever it wants. It doesn't count in the statistic. And then in the denominator, we have a measure of variance. We have the sum of square deviations from the mean divided by the number of observations. So this looks very similar to a Pearson cross-product correlation, but it isn't, and that's important to know. So looking at this a little more closely, this may seem very weird. So in the numerator, we don't divide by n square. Even though we take all the pairs of observations, we don't divide by n square. Instead, we divide by this s sub 0, and s sub 0 is actually what we should be dividing by, because it is the number of actual neighbors among all these possible pairs. So if you sum all the elements of the weights matrix, that in essence counts how many pairs of neighbors there are. So we adjust the numerator by that to take the scale out. We adjust the denominator by n to end up with a measure of variance. So the ratio of these two is a measure of correlation. And so, as I mentioned the other day, a statistic is nothing but a summary that you compute from the data, and because it is from the data, it has randomness in it. And the challenge for any statistic is to figure out whether the value that you observe in your data is special in some fashion. So is it likely that this value is generated by your null hypothesis of spatial randomness? So how do we do this with Morans Eye? We have this cross product in the numerator and the squares in the denominator. Even if we assume nice things like a Gaussian distribution, independent under the null, it's really not that easy to analytically derive what is the ratio of a cross product to a square. This is one of the assignments that I got when I was in graduate school, and I can tell you it's not easy to do. It's possible to get an exact distribution for the statistic, but it's unwieldy, and it's particularly unwieldy because you basically have to compute it again every single time. So it's not like you have a z statistic or a chi-square where you know what it is. This you actually have to figure it out. So my preference is to, and in any case, the practical implementation of these distributions end up all being approximations. So there's two basic approximations. One is assuming normality. The other one is assuming equal probability. So every observation is equally likely to be at any location, which is called the randomization assumption. And then analytically, you can derive mean under the null, what would be the variance under the null. Go further and try to derive the full distribution, or you can just throw up your hands and say, okay, let's approximate this by a normal distribution, which is typically done in practice. So that's the analytical approach. the, you know, the calculations for the mean and the mean is simple. The variance gets a little complicated. But then there's another approach, which is computational. And I've already alluded to this a number of times. We basically will create a set of data sets that conform to the null hypothesis by randomly reshuffling all the observations. So we mimic what spatial randomness would be, and for each of these fake data sets, we compute the statistic, which then gives us a reference distribution, and then we compare what we actually measure in the data to that reference distribution. And this, very confusingly, is sometimes referred to as randomization, which of course is the same word as the randomization that we just talked about in the analytical approach, or preferably permutation. Permutation is clear. You permute the data, and then it's a permutation test, which is, it's just a special case, larger family of computationally driven test approaches based on permutation, based on reshuffling the values. So then another thing is that the statistic itself, and this is very confusing, apparently, especially if you come from a Pearson correlation kind of world. A Morans Eye statistic as such is not comparable. So if you say my Morans Eye is 0.5 and somebody else has a Morans Eye of 0.3, the one with 0.3 could actually correspond to stronger spatial autocorrelation than the one with 0.5, which is completely counterintuitive because it has to do with the weights. It's about interaction, and interaction combines the weights with the parameters. So the Morans Eye coefficient as such doesn't really mean anything unless you know what the weights are, right? However, if you have its mean under the null and you have its variance or the square root of the variance, which is equivalent, then you can convert the statistic to what we call a z-value or a standardized value. And these z-values now are comparable because the computation of not so much the mean, but especially the variance, takes into account characteristics of the weights. So that has been controlled for. So once you turn it from this original Morans Eye that looks like a correlation coefficient but isn't, to the z-value, then you can compare the z-values between different data sets, between different variables, between different weights matrices. So very important to keep that in mind, that the Morans Eye as such is not really comparable. So this is our data set. We'll talk about this more in the lab. But just to set the stage, I compute Morans Eye for the house prices in our data set, and then using two analytical approaches, here are the summary characteristics. So the statistic, of course, is the same, because the statistic has nothing to do with these assumptions. And the mean of the statistic is also the same. The theoretical mean of the statistic under the null hypothesis, again, this is kind of strange, is -1 over n minus 1. So it's not 0. For a correlation coefficient that you're used to, the mean, it's centered on 0 and it's symmetric in both directions. The spatial correlation, the Morans Eye, is not centered on 0. It's a little bit off to the negative side, but of course it's -1 over n minus 1. As n becomes larger and larger, this for all practical purposes goes to 0. But it starts off in finite samples, it's a little bit to the negative of 0. And the theoretical mean is the same whether you take a normal assumption or a randomization assumption. That doesn't matter. The variance does matter between the two. And it's very interesting. The variance for the normal assumption is, if I remember this correctly, not affected by the weights, but the variance for the randomization assumption is affected by the weights. We'll see in a second whether that's correct or not. But then we take Morans Eye, subtract the mean, divide by the square root of the variance, and we have our value. And then we can compare them. Okay, so the permutation approach, as I mentioned a couple of times already, Very simple to implement, but it requires computation. So you reshuffle the data set, recompute the statistic, and then make a graph of the reference distribution. And so in our example, same example, the blue curve and the histogram that's behind it is what we get for Morans Eye for 999 randomly because we compute something called a pseudo p-value. And it's not a real p-value. It looks like a real p-value, but it isn't because it's based on computation. So what we do is we compare the red line, which is the value of the statistic in our actual data set, to the distribution. We count the number of times one of our replicated values is equal to or larger than the red line. In our case, 0, right? Then we take 1 for the one that we observe from the data set, and we divide that by the number of replications, 999, plus 1 for the one from the data set. And that's why we take 99, 999, 9,999. So we get nice looking p-values that aren't some weird fraction of something, even though it's totally arbitrary. The other thing to remember is that the kind of, you can call it the precision of the p-value, even though that's not really the right way to put it, is completely artificial because it depends on the number of replications that you carry out. So if you have the same data set and you do 99 permutations, you say, oh, the p-value is 0.01. But then you do 999 permutations, and then all of a sudden, the p-value is 0.001. So is that more significant than the other one? No, it's the same. And so it's important to remember that this pseudo p-value, that's really a bad term for it because it's not a p-value at all. It's just a summary proportion that tells you how often your replicated, randomly reshuffled data gave you a statistic that was as extreme as the one that you observe for the actual data set. So if you've never done this before, it's easy to fall into this trap, fixated on these pseudo p-values as if they were real p-values, but they aren't. And just to give you a sense, go back to this table and see the real p-value based on an analytical approach has many more zeros than 4 of them. So this is highly, highly not spatially random. And as I said earlier, that's what we expect because most phenomena in real life are not spatially random. So we expect to reject this null hypothesis. Okay, how do we interpret this? And a couple of things that are, again, not standard. First of all, I mentioned the theoretical mean is -1 over n minus 1, so it's not 0, but basically it gets close to 0 as we get larger and larger data sets. The interpretation of the alternative hypothesis we talked a little bit about last week. So if it's positive and significant, then it points to clustering of like values. As I mentioned the other day, not high or low, could be both or some combination, right? So clustering of like values and negative and significant alternating values, checkerboard, presence of outliers, spatial heterogeneity, more variability than you would expect under the null. So very important that this is a global property. I know I've said this before, but you wouldn't believe how many times I see this interpreted in the wrong way. It's a global characteristic of the data. It's not about clusters. It's about clustering as a property of the data. Also, if it's not significant, then it's not positive or negative. That's another one that I see a lot. You know, people write up the results. It's Morans Eye is positive, but it's not significant. It doesn't have a sign. Not significant, it means it's spatially random. And so for all practice, it doesn't exist. So it's not positive or negative, it's nothing. When you compare them, as I mentioned before, very important to keep in mind that the magnitude of the coefficient depends on the weights. And as long as you have the same weights and different variables, you can compare them. The moment you have different weights, you cannot compare them. And as I mentioned before, using the mean and the variance, you convert them to z-values. The mean, not the mean, the variance incorporates characteristics of the weights, so then the z-values are actually comparable. And just to illustrate this, this is the same data, 3 different weights. So the top row gives you Morans Eye. They're all pretty much in the same ballpark. They're a little bit different. And you would think that based on this value of Morans Eye, the one given by the K6 nearest neighbors is the strongest evidence of spatial autocorrelation. So then we do the mean. The mean is the same. The variance is not the same. That's where the effect of the weights is being incorporated. And so as a result, the z-values won't be the same either. Then if we look at these z-values, we see that in fact the measure based on the distance weights gives the strongest evidence of positive spatial autocorrelation. So the Morans Eye as such, not comparable. Once you turn them into the z-values, you, in a sense, correct for the differences between the weights, and then they are comparable. So very important to keep that in mind when you write up your results. So as I mentioned, it's about clustering, no location of clusters. I say that so much because I see it all the time, you know, and you better make a note of it that when you write up your results, when you do your project, that you don't refer to clusters when you do a global statistic. You can't, even though you look at the map and you think you see a cluster, you run Morans Eye, you say, it's positive and significant, I have my cluster. No, you don't. You won't have it till next week. Next week we do local spatial autocorrelation, which will get you the cluster. Some really more philosophical problems. There's this notion of true versus apparent contagion. And this has to do with what in the literature is called the inverse problem. And it's the difference between pattern and process. So process is how something works. Pattern is the outcome. And so one of the problems, especially with cross-sectional analysis, is that we get a pattern, but we have to figure out how did we get there. What was the process that gets us there? And you know, it's the same in a lot of sciences. You get an archaeological dig, you have to figure out how did it get there, right? What was the process that got us there? Difference. You can do the pattern, measure autocorrelation all you want. That doesn't tell you how you got there. And one of the problems, especially in cross-sectional data, is very different types of processes that can give you the same outcome. One is what you like to think is a process of contagion, mimicking peer effects, spatial diffusion, spatial interaction that gets you groups of observations that look alike. That's what your spatial autocorrelation will give you. And that is the natural interpretation, but sometimes incorrect interpretation. Because the same outcome can be the result of spatial heterogeneity, when there is an underlying factor that makes the process different. And in my other class, we were talking about John Snow and the cholera epidemic. And so this is an example where, I mean, he was lucky, but there's a tension between apparent and true contagion. So one explanation of the pattern would be that somebody who was infected moved into the neighborhood and infected everybody else. So you see a grouping, more disease than you would expect randomly, so you reject a null. The other one is that everybody drinks the bad water from the Broad Street pump and gets sick. Spatial heterogeneity, right? A different type of explanation. So the key concept here is that, especially with cross-sectional data, you can't tell which of the two it is. And so again, this matters when you write up your results. When you interpret the results, you're dealing with a pattern, you're not dealing with the process. To deal with the process, you either need space-time data or multiple sets of cross-sections that can somehow be categorized along different variables. You need more information. That's the bottom line. And this is a major problem when you deal also with cluster detection and explaining why the clusters are there. What is the process that gets you the cluster? Okay, Geary C. So Morans Eye, cross-product. Cross-product, as we'll see in a few minutes, has a direct relation with a regression linear association. We're very comfortable with that. Geary C is focused on dissimilarity, which is not the same as similarity. It's the opposite. So when the values are small, the two observations are more alike. When the values are large, they are not alike. So Geary C uses square difference as the measure of attribute similarity instead of the cross product. And in that sense, it's but not equal to the notion of the variogram, which we'll see a little later. The main difference between the two is that with the variogram, we take the distance as the organizing concept to formalize locational similarity. And with Geary C, we have a weights matrix. So again, the statistic looks a little complicated. Actually, isn't that complicated. The numerator, again, we see the double sum. We see the weights, which really means that we only count the neighbors. The other ones are not counted. We see the square differences, and we divide it by some factor to rescale things. And the 2 in there is really to rescale it such that the mean of Geary C is 1, not 0, 1. Yeah. And then the denominator is the same as before. This time we divide by n minus 1, which makes it an unbiased measure of the variance, not a consistent one. And again, the mean effect is expression that I have in the slide is the textbook one. And it can be, if you look at it very carefully, you might say, hey, why does he have x in the numerator and z in the denominator? It's because it doesn't matter. Because you take the differences, the means get washed out. So whether you express this in the original variable or in deviations of the mean, it's the same. And so in the textbooks, it's often written like that. Of course, in practice, if you've computed the deviations from the mean, you're going to use them in the numerator, and in the denominator, it doesn't really make a difference. So, as I said already, is the flip side of Morans Eye. Morans Eye, positive is positive autocorrelation. Here, positive is negative autocorrelation, and negative is positive autocorrelation. Why? Dissimilarity, small dissimilarity is alike. Alike is positive spatial autocorrelation. So the mean of Geary C, and this is one of these other weird things, is not 0, it's 1. If you have smaller than 1, below the mean, or you use the standardized form, the z value, that is negative, that points to positive spatial autocorrelation. And the reverse, of course, points to negative spatial autocorrelation. So to me, as long as you know that, it's not more confusing than the other one. It's just a way of thinking about it. But it's important to appreciate the difference between these two. They're not the same. A lot of times when you look at this at first sight, they often give you the same indication, the same conclusion, but not always. And why not always? Because they really measure different things. The Morans Eye is all about linear association. The GeoDa doesn't need that. It doesn't need the linearity because it's based on, if you think about it, the square differences is a measure of distance in attribute space. So if you think of one variable and you have two observations on a line, one is here and one is there, how far apart are they? That's what GeoDa measures. The square difference between their values is, you know, in geometry, what the distance would be on, later we'll see how we can extend that to multiple variables, but it's the same concept. So GeoDa is really all about distance in attribute space, whereas Morans Eye is about a slope. It's a slope of linear association, as we'll see in a few minutes. So inference, same thing. You can do a lot of algebra and do analytical derivations and then use approximation. It gets a little complicated with GeoDa, or you can just do a permutation approach and then a reshuffle. Again, same example. Notice all these values for C are less than 1. So they suggest positive spatial autocorrelation. It's not because that they're positive that it is positive spatial autocorrelation. If you had 1.2, that would point to negative spatial autocorrelation. So it's with reference to 1 that you have to compare them. You see, the mean is 1 no matter what assumptions you make. The variance differs. That's where the effect of the weights is taken into account. And then the Z values differ as well. And in this case, the ranking for Morans Eye. So again, if you look at the coefficients on the top row, the smallest value, which is the population, is the nearest neighbor with 6 neighbors. But then by the time we get to the Z value, the most negative positive spatial autocorrelation is for the distant band weights, which is exactly what we found for Morans Eye. This is our reference distribution, and you know, as opposed to Morans Eye, where our statistic was on the right-hand side of the reference distribution, here it's on the left-hand side. So it's much smaller than anything else we simulated by reshuffling the data, which clearly points to it being significant. So as I mentioned, the main difference between the two is that Eye is a cross product, so it's, you know, just like a correlation coefficient is related to a regression coefficient. We're very comfortable with that notion. But that's not always the best notion to use, because if we have highly nonlinear features, then Morans Eye may not pick it up, whereas GeoDa, this linearity, it's all based on distance, might be able to pick it up. So they're not the same. So Morans Eye, I don't need to recap, we just did it, but if we go a little lower and do a little bit of algebra, especially if we row standardize the weights. Row standardizing, just to refresh your memory, means that each row of the weights matrix sums to 1. So the sum of all the weights is the sum of the rows. So each row's sum is 1. We have n rows. So the sum of all the weights, 4 row standardized weights, is the number of observations. And we see in the expression above, we have n in the denominator, then s sub 0 in the numerator. These two cancel out. So everything looks a little simpler. And if you remember your algebra from a simple bivariate regression slope, that's what Morans Eye is. So Morans Eye is the slope in a regression, but not the regression that comes natural. The natural regression is the value at a location regress on neighboring locations. So that would be the Zi as the dependent variable and the spatial the equation bias, as it's called. So you can't use ordinary least squares to regress that slope. The slope is biased. But if you flip it around, it's not. And in fact, given that the z-squares are in the denominator, you need to flip around. So the dependent variable is actually the spatial lag, and the explanatory variable is the value at a location. So it's flipped around, but once it's flipped around, you have a scatter plot. You know, every pair of a value and its neighbors is represented as a point in that plot. And then you can fit a linear line through the scatter plot, as we've already seen in the lab a couple of times before. And the slope of that line mathematically is Morans Eye. Should you do a significance test using regression statistics on this? No. Okay, very important. That's not valid. It is a regression, but it is not the kind of inference that we do for the spatial autocorrelation coefficient. So we still need to do the permutation to figure out what the significance is. So this is very easy to do, and we'll this is the same example again. The linear fit is the line. The slope of the line is given on top, 0.282. That's Morans Eye autocorrelation coefficient. A couple of things that you can do. So you can't just look at the traditional t-statistics for this, but you can use this as a diagnostic for the extent to which particular locations may be driving this slope. And in particular, in the Cleveland example, I don't know if you looked at the data at all a little more carefully, but there's this one sale, about 500,000, that is just totally non-representative of the rest of the sales. So this point is way out there. And if you think of regression, I don't know how much regression analysis you've had, but there's this notion of leverage points. So there are certain observations that have maybe a disproportionate effect on the slope of this regression. And you know, we can, you know, using GeoDa, for example, you can kick this point out and redo the analysis and see the effect on the slope of kicking this point out. And you can do other such things, looking at the influence of particular observations. Another classic example is when you look at international data. Some work I did a long time ago, we looked at conflict in Africa and African countries. At the time, Sudan was still one country, and so Egypt was Sudan's neighbor and Sudan was Egypt's neighbor. So there was no averaging going on in the computation of Morans Eye. It's just one neighbor. And you will tend to find that these are kind of high leverage points in the computation of the statistic. Now, if you have a lot of observation, it all kind of gets washed out. But if you have smallish data sets, this can make a big difference. In the Africa case, it did make a big difference. So one thing that this Morans scatter plot allows you to do, as I mentioned in the introduction, is start to make the transition from the global thinking to the local thinking. Okay? And how do we do that? We do that by centering everything on the mean. So these variables are all standardized. So the mean is 0, and these are actual standard deviational units. So look at this. This is going to be about eight standard deviational units away from the mean. So by any definition, that is an outlier. So we center them on the middle, and then we think about categorizing the type of association into 4 quadrants. As 2 quadrants, top right and lower left, correspond to positive spatial autocorrelation, and the other ones correspond to negative spatial autocorrelation. And then you can refine it even more and think about the top right quadrant is high values in the sense of above the mean, surrounded by neighbors. The spatial lag of the neighbors is the average, that are also above the mean. So we call that the high quadrant. But keep in mind that this is just relative to the mean. If the mean is very low, then high is not going to be that high, right? And, you know, it's all relative to the mean. And this is important when you do this over time, and we'll talk a little bit about that in the every time you do this. So even though you go down over the years, you're on the mean, so high, even though you were 10 years before. That's something to keep in mind. So high is positive. Below the mean, with neighbors below the mean, is low, also positive. And these correspond to notions of clustering. And then next week, we'll specialize this to specific locations in these quadrants, which will be clusters, locations surrounded by other similar locations above the mean, high, and below the mean, low. Then the two other quadrants are what we call spatial outliers, or what I call spatial outliers. These are here in the lower, this one, right-hand side, the value above the mean, surrounded by neighbors below the mean. So this is a spike surrounded by much lower values. And then above is the other way around. It's a dip surrounded by higher values. So a lower, below the mean value surrounded by neighbors above the mean. So this we call high-low, the other one low-high. So the visualization of the Morans Eye coefficient in the Morans scatter plot has two aspects. One, the slope of the linear fit is the statistic. So steeper slope, higher statistic, negative slope, negative statistic, and so on. But secondly, it allows us to start categorizing the type of spatial autocorrelation, whether it pertains to values above the mean or below the mean, surrounded by neighbors above the mean or below the mean, and the categorization of locations as potential spatial outliers. So to summarize, we have the four quadrants, positive spatial autocorrelation, like values, negative autocorrelation, outliers. I call them spatial outliers. Here they are. And then, of course, given the linking architecture behind software like GeoDa, we can do linking to find out where those things, where those locations are. And these are the outliers. Then we can do other fun stuff with the Morans scatter plot. It's basically do anything that you can do with any scatter plot. And one is why stick to the obvious linear fit is Morans Eye. So good reason. But we might be interested in structural breaks, spatial heterogeneity, especially if these structural breaks have a geographical spatial interpretation. And as it turns out, one of the examples I concocted for the lab, it's perfect. You know, you can really see the difference between the degree of spatial autocorrelation in different subsets of the data. Here, it's a little mixed. There's clearly something funky going on, but you know, that could be in part because of the outliers. I removed them. Yeah, in this I removed them, but still some indication of a positive slope in part of the data. And then once we get beyond these really high values that are more than one standard deviation above the mean, there is much less evidence of positive spatial autocorrelation. We would want to see where are these sales, and is there anything about these transactions that's different from the other ones. In the, if I can call it the classic Columbus example, which I used way back when to illustrate spatial autocorrelation, there's actually a way to divvy up the data so that part of the data has spatial autocorrelation and the outlying areas don't have any at all. So there, you know, it's crime statistics. So You know, the core of Columbus has a lot of crime and is very correlated spatially. Once you move to the outlying areas, there's no spatial autocorrelation whatsoever. So then again, that points to heterogeneity. You have to take this into account to build for the data. So in a interactive dynamic graphics kind of sense, which we've seen before, this is how you use the lowest smoother to characterize potential structural breaks in the nature of the spatial autocorrelation. So we've seen Morans Eye, crossproduct, and its visualization in the Morans scatter plot. We've seen Geary C, square deviations. Both of them rely on the weights matrix. A lot of people don't like the weights matrix. They find it's counterintuitive, it's arbitrary. Where do these neighbors? You can see where I'm coming from. Somehow, distance is deemed to be superior. Actually, it's the same thing. There's no free lunch. You're trying to model interaction, and you don't have interaction data. So whether you put in prior structure through the weights, or you put in prior structure by sorting everything by distance, there is still a prior structure. And so one way to approach this is a totally data-driven way. And we call it a nonparametric correlogram. And it's nonparametric because there is no model. So Morans Eye has a cross product and some connection to a regression slope. Geary C is a square difference. Here we let the data drive the shape of the association. So both Morans Eye and Geary C, one coefficient for the whole data set. Here we're going to fit a curve. So this is a little bit different when there is no nonparametric autocorrelation coefficient, but there is a nonparametric autocorrelation curve, which we call the spatial correlogram. And unfortunately, again, there's a lot of confusion about the terminology. Sometimes a correlogram is used to designate a series of autocorrelation coefficients computed for increasing orders of contiguity. So you will see this in the literature. Say we have our prices, we do first order contiguity, Morans Eye, second order contiguity, Morans Eye, third order. And so if you show these in a graph, that is also called a spatial correlogram. Okay. This spatial correlogram is different in that it's more related to the concept that comes from geostatistics, which we'll see in a few minutes. So we use the actual correlations in the sample. And how do we do this? Well, in general, and typically we do this for standardized variables to get rid of the effect of the mean primarily, and also a little bit the effect of the variance. So any cross product of variables, if they're just in deviations from the mean, we have to rescale them by the variance, but if they are in standardized units, we can just multiply them. That's an estimate of the covariance, or if they're standard of. But that doesn't get us very far. That doesn't get. It's the same incidental parameter problem that I talked about the other day. So we can't really have a different parameter for each possible pair. So we have to organize this somehow. And one way we can organize it is to make this covariance, spatial covariance, or correlation, depending on whether the variables have been standardized, a function of distance. And not a specific function, not like, inverse exponential or something like that, but a function that's dictated by the data. And we've already seen this concept a few minutes ago in our local regression curve. The local regression applied to the scatter plot fits a different kind of regression using a subset of the data, so it follows the variability in the data much closer than, say, a linear fit, which is one slope for all. So there are a number of different ways in which you can do that. Local regression is one, kernel regression is another one. So the essence is that there's no functional forms pre-specified by the data. And if, this works well if you have a lot of data. If you don't have a lot of data, this doesn't work very well. So in general, it just says the correlation between I and j is some generic function of the distance between I and j. And the way we deal with this is you can think of a graph, and I'll show one in a few minutes that's a little bit different, but think of a graph with all the correlations. On the vertical axis is the value of the correlation. On the horizontal axis is the distance separating the points. So every pair of points every pair of locations is a point in that graph. The higher, the more correlation. The lower, the less correlation. The further out, the further apart they are. The further to the left, the closer they are. And then we take all these points and we can fit a curve to it, just like we do with a lowest curve or a kernel curve. You just fit a non-parametric curve to it. So that's the principle. You have all these cross products. To explain this is that if you're all familiar with the notion of a variance, is always positive. There's no such thing as a negative variance. So once you extend this notion from, a univariate context with the variance to a multiple variable context, you have variance covariance. And the counterpart of having a positive variance is that you have to have a positive definite variance covariance matrix. In a nutshell, it means the determinant has to be positive. It's not just a property of the variance itself, but it's also a property that includes all the covariances. And one of the problems with this non-parametric is that it does not guarantee the structure of the variance covariance matrix that you end up with is actually positive definite. Now, that's a bit of a technical notion, but it does mean that if you're not careful, that you can end up with nonsensical results, like negative variances, the counterpart of negative variances. The other thing is that it doesn't necessarily respect Tobler's law. Tobler's law is everything correlated with everything else, but for closer things more so, or translated, further less so. So you want to see a decay in the spatial correlation with distance. And because this is non-parametric, there's no guarantee that the slope actually goes down. It can go down and up and up and down, as we'll see. So one way to implement this, I mentioned, is to fit a local regression curve, a lowest curve, or a kernel kind of fit on all the pairs. A simplified way, because remember, pairs is n squared. So that's all good and well if you have 40, 50 observations. If you have 100,000, that's a lot of pairs, right? So it becomes a little unwieldy very quickly. So what we do in the GeoDa implementation is we bin them. And you'll see in a few minutes the counterpart of this in geostatistics. So basically, we divide the range and then put all the pairs that are within that bin, and then spatial correlation for them, and then fit a local regression curve through these points. So every one of these little blue dots is the average of the spatial correlations of all the pairs in the distance bin that corresponds to it. And one of the things notice is that this is not a simple distance decay. In fact, it goes down and it comes back. Now, why would that be the case? Well, two reasons. And they're basically related to the same thing. As we move up in the distances that separate the points, these bins get smaller and smaller. So that's the nature of the distribution of pairs of points. There are, not all the points can be very far away from each other. So the points that are truly far away from each other, there's very few pairs in those bins. That means that the precision of the estimate goes down. Because these blue balls, they're just estimates for the correlation. So as you have more pairs in the bins, the precision of the estimate will be better. As you have fewer pairs in the bins, the precision of the estimate gets worse. So in other words, whether that blue dot in the last bin is actually effectively under the zero line, we don't really know, because it may be so precise that for all practical purposes it could be zero. So that's one aspect of this. The other is related to this, and is Tobler's law. As these points get further and further away from each other, in fact, they shouldn't be correlated at all. What we're doing here is having an imprecise estimate of what should be zero. So that's why there are a lot of rules of thumb, and we'll talk about this in the lab, to cut the distance, adjust the distance over which you evaluate these pairs, mess with the number of bins, and all this kind of stuff that we'll talk about in the lab. So this is an example of, as you shorten the distance, it's easier to see the shape of the curve. What is the most important aspect here? It's not so much the magnitude of the correlation, which is really the focus in Morans Eye and Geary C, but it is the range of the correlation. So for all practical purposes, once we cross the zero line, we can say that pairs of points further away from each other than that distance, which we call a critical range, are no longer spatially correlated. Whereas it's useful if you want to subsample points that are not spatially correlated. You just make sure that they're further away from each other than this critical distance range. So if this is useful in a big data world, if you have lots and lots and lots of data points and you want to use traditional statistical analysis that requires uncorrelated observations, you figure out what is the range of the spatial autocorrelation, and then you resample points that are far enough from each other that they are in fact uncorrelated, and then you go back to your standard techniques. Now, of course, if you only have 40 observations, you can't do that. This only works in large data settings. So, as I mentioned, it's an alternative to using spatial weights. We use distance instead. There's a whole bunch of technical issues that I may have time to talk about in the lab, but they're beyond the scope. They have to do with they're generic technical issues of how you fit a local regression curve, what kind of kernel function do you use, what kind of bandwidth do you use, those kinds of things. We talked a little bit about that in the context of the lowest fitting to a scatter plot, but it's all the same thing. So I really like this as a quick and dirty sense is the range of interaction that we might have in the data. And if you have lots of data, like in typical real estate transactions, you have hundreds of thousands of data points. If you want to do an analysis that is free of spatial autocorrelation, you figure out the range of interaction, you resample, and you're good to go. Now we switched gears again. So we started with the weights, then we got rid of the weights and we used distance. We didn't have any function, but we still use cross products. Now we're going to distance again, but we won't use cross products. And this is actually, could be a whole course in its own right. And in fact, it typically is. So here I spent 15 minutes, anything you ever wanted to know about geostatistics, right? The concept, the critical concept in geostatistics is a variogram function, or more precisely a semi-variogram. But it doesn't really matter. I mean, it matters to people in geostatistics, but as we'll see, it's just a matter of dividing by 2. So you divide that by 2, This is the half a variogram, the semi-variogram. The one on top is the full variogram. As long as you know which is which and what you're talking about, we're all good. So variogram comes out of mining, actually gold mining. And it's really methodology underlying a particular form of spatial interpolation. And just think of the situation where you work for a mining company, or, you know, this is a big deal in the oil exploration. So you're going to drill for oil. It costs millions and millions of dollars to do a test drill. How many test drills are you going to do? And how are you going to estimate how much is under there based on the results of drills? So you can think of drills as sample points, and of your estimate of as a spatial interpolation, typically in reality in 3 dimensions, but we won't go there. It's the same thing. So it's basically, how do you get a sense of the function that you can use to interpolate spatially, meaning coming up with values for locations that you do not observe. This is the same problem as, say, air quality measurement in a city. You have sensors, you know, the array of things is going to deploy a bunch of sensors in the city. How do you assess the air quality for locations that don't have a sensor, right? So probably there is something systematic in the correlation between these values, systematic across space. And that's the notion, that's the idea behind this variogram, which is actually much more robust than everything we've done so far, because again, just like Geary C, it doesn't use cross products. Remember I mentioned in Geary C, whether you take out the mean or not doesn't really matter because it gets rid of it. So you don't need to make any assumptions about the mean. Here's the same thing, you know. So it's a very strange concept, right? Strictly, I mean, you'll see in a few minutes it's actually more intuitive than it looks at first sight, but it's the variance of the differences across space. So it's not, so we have air quality measures, right? One here, then one, you know, a mile away from it. It's not the variance of these measures. It's the variance of the difference between these two measures that are a mile away from each other. And in a few minutes, after a little bit of algebra, we'll see what it boils down to. So that is called the variogram, and the underlying assumption is that somehow this measure, this summary of the data, shows systematic variability with the distance of separation between the points, the locations to which it pertains. And the distance of separation, so S summarizes the location, S plus H is a move away by distance measure H from that original location. What is the variability of the difference between the two measures? And then you divide it by 2, it's the semi-variogram. So if we do make a constant mean assumption, then the mean of the differences, which is the difference of the means between, because the means are the same, is 0. So then if you remember your stats, the variance of a difference is the expectation or the mean of the squares minus the squares of the means, right? And the squares of the means is 0, so you end up with the mean of the squares. And now we're back in business. Just like for the correlogram, we binned our pairs and we got the average cross product for all the pairs in the bin. Here we're going to bin our pairs and get the average square difference for all the pairs in the bin. And that is the semi-variogram. However, unlike the correlogram, where correlation gets smaller as we move further away, since we're measuring square difference, we're measuring dissimilarity, the dissimilarity will go up as we move further away. So the correlogram goes down, the semivariogram goes up as we move away with distance. So how can we summarize this? A couple of different ways. GeoDa doesn't do this. Why not? Because we don't want to reinvent the wheel, and there's fantastic software already out there to do variogram analysis and geostatistical analysis. If we have time in the lab, into GStat, which is really a very good package in R to analyze this. But in any case, you have my notes, so you can do it on your own. So one thing, again, is to throw everything out there. You know, just like I mentioned for the correlogram, we could have all the pairs, or basically half, because they're symmetric. And then just kind of look at this, right? And this is called a variogram cloud plot. And that's what it looks like. It's a mess, right? Because there's so many pairs. Basically, the bottom part is all clogged up. You don't see anything. And you're basically not really interested in this bottom part. What you are interested in are outliers. And outliers in the following sense. So these observations on the left side of the graph are not very far apart. So therefore, they should be very similar. Their dissimilarity, which is the square difference, should be very small. So if you have a point here that has a very small distance but has a large square difference, you say, what is going on here, right? And then in GStat and other similar software, you can identify these pairs. So for example, we click on a point over there. Each point corresponds to two observations, not one observation. And then we can identify them in the point map. And we see, for example, that these are points that are very similar and very far away, or very dissimilar and very close together. So these are the kinds of exploratory things you can do with the variogram cloud plot. The example, I think these is the house prices. So it identifies these couple of transactions that are way out of line compared to the other ones. Another example I use a lot is air quality measures in Los Angeles. If you're familiar with Los Angeles, it's a basin. That's why they call it Los Angeles Basin. At the edge of the basin are mountain ranges, and you go over the mountain ranges, there's a desert, right? So some of these sensors are on each side of the mountain range. But the air quality is very different. So there's basically a break, structural break in the air quality. But they're very close together. So in the rationale of the variogram, or also the correlogram, as similarity decreases with distance, or dissimilarity increases with distance, these two sensors, these two measurement stations, are very close together and show very different measures on each side of the mountain range. So that's something you have to take into account of your modeling. There's no way you should use these together. You should somehow model the structural break in whatever you do. So that's what you use this for. So then we have this notion of an empirical variogram, which is very similar to the correlogram that we just saw, but just like Geary C relative to Morans Eye, one is cross product, the other one is square difference. This, again, is based on square difference. And we bin pairs in a distance band, and we take the average of the square difference between them. And very similar to what we saw before. So now we have these little quotas with values of the square difference. The square difference goes up as the distance between the pairs increases. Just like I mentioned before, there's a bunch of rules of thumb. I'll talk about this in the lab. Half the maximum distance, a third of the diagonal of the bounding box, at least 30 pairs per bin, all this kind of stuff. The bottom line is, because these are summary estimates, the number of pairs that you take into account. So at some point, it doesn't matter anymore if you have thousands of pairs. the difference in precision is not going to be a big deal. But if there's very different densities, if you wish, in each of the bins, then the precision of these values will be very different. And then any pattern, regular pattern that you might expect will be very hard to detect because of the imprecision of the measure. Just a couple of quick things. It shouldn't keep going up. It should flatten out, because at some point there is no more effect of increasing distance. If you're not correlated, you know, whether you're 50 miles apart or 200 miles apart, you're not correlated. So it should be flat, right? This one is not flat. This, in practice, tends to point to the presence of a trend in the data. So to get out the trend, you basically use a regression and then do the analysis again on the residuals of the regression. That's a little too technical, but you know, you see it gets flatter and flatter as we take residuals of a model, in this case a trend surface model. So the idea is to use this empirical variogram to inspire a model for the change of dissimilarity with distance. But before we go there, yeah, so you can read all this stuff. Before we go there, very important assumption is this assumption of isotropy. And isotropy means that the only thing that matters is distance, and orientation doesn't matter. Now, geostatistics is a big deal in the natural sciences, not so much in the social sciences, but in the natural sciences. It's used in soil science, it's used in meteorology, I can't say that word, but climate science. And there, the assumption of isotropy doesn't necessarily hold. Even in air quality, it doesn't hold. There's prevailing wind directions, and you know, for example, in the LA basin, the wind comes from the ocean or from the desert is going to make a big difference. So one of the things that you have, and if we had more time, we could explore this in further depth, is the extent to which this assumption actually holds. And there's a number of devices that allow you to do this. If we have time, we'll go over this in the lab, but just to give you a sense, one is to split up the pairs of points, but also by distance and direction. You know, the angle of separation. Are they horizontal angle? And then you do basically take subsets of the pairs and have a separate variogram for each of these. And if there is no directional effect, they should all look the same. Right? Another way of doing this is to go even further, and rather than just taking direction, angular ranges, and distance, you combine the two. So you have basically each of these little boxes shows separation in both distance and direction. And again, what you want to see is nice concentric circles. So that means there's no directional effect. If you see these kind of elliptical bands, it gives you evidence of directional effects. One of the problems with this is that these bins get really sparse very quickly. So then there's all kinds of tricks, which we can see in GStat, the software, where you eliminate the ones that don't have enough pairs, and still you have even stronger evidence of some form of directional effect. Okay, what is the end of all of this is a model. In 2 minutes, everything you ever wanted to know about variogram models. Some strange terminology. We also saw the notion of a range. So range is basically distance beyond which autocorrelation, spatial autocorrelation doesn't matter anymore. SIL this comes from mining, is another word for the variance of the process, the total variability in the process. And the nugget is totally bizarre. That is just a measurement error. That is, there should be no variance as distance 0, but in practice, because of lack of pairs at very small distances, there's always a little bit of a rounding error, and that's called the nugget. So the ideal theoretical variogram looks something like this. You see a slow, continuous increase of the dissimilarity with increasing distance up to a point, the range, and then it's flat, right? Of course, you saw empirical diagrams, they don't look anything like this, right? So then there are a number of models. Remember this thing about the positive variance, so they're valid variogram models, that they're mathematical expressions as a function of the distance that have the right property in the sense that they have a positive definite variance covariance. Because these are squares, again, it's flipped around. It has to be a negative definite variogram. We won't go there. But these are a couple of the most commonly used. Spherical one is a classic one up in the upper left-hand corner. The exponential one is also used a lot. Gaussian one. Then this is the wave. There's all these weird ones that can account for strange phenomena. They're really having to do with different scale effects. Some things work on smaller scales, some things work on intermediate scales. So this is just a little bit of terminology. And then the end result is that in practice, you want to fit one of these to the points in your empirical variogram. And again, you can spend a whole course on how you do this and all the different complications of heterogeneity, precision, robustness. And then once you have this function, then you're in business. Because then you can use this to do spatial interpolation, because you can, for any distance, get an of either the square difference or related to this with a little bit of math, the covariance, and then you can relate the value at a unknown location to observed values at known locations in function of the distance to those known locations. And that gives you the tool for spatial interpolation. And I did it. 70 slides. I promise I won't do this again.